let's jump into, DLV3. I got a few things running last time, so let's quickly look through the paper. Can I not move this? Yeah. Okay, cool. Anyway, and then we can look at the code. So just to quickly kind of go through what DLV3 kind of introduced us was to this new dilated convolutions or true convolutions, which was just convolving with a different rate. Or in other words, these red dots are the ones where your weights are, and the rest of it is kind of zeros. So with rate equal to 6, you basically have like 5 zeros between two of these red pixels. And they kind of changed the rates. So the idea behind that was that the bigger the window, the more you're able to see, so the more context you gain. But if you were to naively just increase your window size, the problem is the weights would increase, and as window increases, computation size would increase. So this strategy basically gives you the benefit of looking on a wider range, but at the same time keeping to exactly the same number of computes. So you'd still have just 9 multiplications kind of going on. You're not changing that. The other things was that you don't start from, or you don't perform this this pyramid pooling at like every layer, or as you go down the, let's say the resonant block. What you do is you either go down to where this is like 16 times smaller than the width and height of your original image. So that would be like a bunch of convolves pools. And then when the width and height kind of become 16, or I think they even have an example of 8 is when you kind of do it. Pros and cons of that: when you do it at 8, you're going to obviously have much more compute, so it's going to take longer, though the results are going to be slightly better versus that of 16. And then what else was there on this paper? I wanted to just kind of, this diagram is what I like better for. Let's look at just the top, the DLV3 plus paper. This is though, but we won't be doing the plus part today. The encoder side, encoder decoder part of it. So this is, very straightforward. Do a 1x1 call, 3x3 con, rate 6, 3x3 con, rate 12, rate 18, do a last image pooling. This one actually would be a 1x1, which you interpolate and bring it back to this size, stack them all up, perform your conv to kind of get n classes on the output side. So that was like a quick whirlwind review. Does that kind of make sense? And then we can kind of look at the code side by side. Any questions there? Or can we jump into the code?
And that's fine, yeah.
All right, sounds good, perfect. Okay, so let's look at the code. Let me pull this up. So yeah, cool. So first part of it here with DLV3, we look at build out this part of it, which is the heterospatial pyramid pooling. So init basically has a setup for all these guys. You have a 1x1 con, a 3x3 con, 3x3, 3x3. So these 3x3s just change with respect to dilation, which is basically what controls your number of holes. Since you want all valid convolutions to be of equal size, you set your padding also equal to be that of dilation. So every time you reach your exterior pixels, you still have like 6 more or 12 more or 18 more kind of fake pixels to kind of give you actual convolution values. You see the input that kind of comes in here is this output from this CNN partway down. So it'll be like, that's what they call that stride, output stride, which is basically input width and dimension divided by wherever you kind of stop in this chain with your divided by that dimension. So that is usually 16 or 8. I think my example currently will be having 16. We'll look at that. Now, so yeah, so these 4 convolves done. Last one is an adaptive pool. So that's just an adaptive average pool 1x1. And towards the end, so we'll stack these together, and then you have these convolves, and those convolves are basically, you have 2 convolves there. You have a 1 convolve, which is a 1-by-1 convolve. Both are actually 1-by-1 convolves. The first convolve is just you're going. Wait, did I miss something here? Actually, let's check into the forward, and then because I'm kind of confused why this is 5, 1, 12. I think this convolve and this average pool are tied together. Let's see. So yeah, this is what I was saying. You start with your h by 16, w by 16 because you stopped halfway. I mean, somewhere down your encoder route. So that's your feature map width and feature map height. Perform your. This is your first one call. So this basically is just kernel stride one, kernel stride one. I mean, sorry, kernel size one. So this kind of gives you a lot of this global context stuff, and you're kind of pulling in all that information there. Your 3x3 cons, just a typical convolution layer. You have your con, you have your batch norm, you have your relu, and all these, the input is the same feature map. That's what is coming in from here. So the same feature map comes in, you perform all these three 3x3 cons, this 1-by-1 con, as well as the image pooling. And you can see that the input which is coming here is basically h by 16. So your stake with your parameters that you've set with padding equal to 6, 12, and 18, you see to that your output dimensions, that is your width and height, don't change. So that's why you get back h by 16, w by 16, and all of them. You're starting with 512 cons as input filters, and you want 256 output filters. And that is what those parameters set are. And then you have the average pool for this feature map that was done. So you get back out image, correct. So that convolve, which was there here, this one is tied with this average pooling. So you perform out image is passed in here. So you do this convolve again here, which will end up basically being a 1-by-1, right? Because you're doing an average pool 2D to size 1. So you'll have just one sort of pixel with just the channel axis or the channel dimension present. So that's why you kind of get back 256 1-by-1. Now you need to kind of stack these together. So you need to bump this guy up from 1-by-1 to h by 16, w by 16. And that's what you do over here. You interpolate. That's what kind of gives it back to that size of h by 16, w by 16. So now if you see, you have 1, 2, 3, 4, 5 of these stacks, and each of them have an output of 256 filters. So 256 into 5 is nothing but 1280. So that's what this column is representing now. So that is saying I'm going to get an input of 1280 filters, spit out 256. But then we know that in segmentation, you always want your output number of filters basically equal to be the number of classes. So that's why you stick this convolve at the end, where it is taking these 256 filters as input and spitting out number of classes. So that is the ASPP block, which is basically the main thing that you need for this DLV3. So is there any question on that, or can we kind of move? Let me check the chat. Srinivas, do you have any questions? Are there any questions in the chat? If someone can pull that up. Oh.
Yeah, there's one. Srinivas
Okay.
says, can you see it?
Sorry, 1 second. I'm not able to find my chat. There we go. Okay. So is a true convolution occurring just because of padding? Rather, it's the other way around, right? You're doing a true convolution is to basically, their theory is that you want to have more global context. Where did that paper go? Right. So this is what you're doing a true because our dilation basically is because you want to keep the number of operations same, but you want to look at a much wider window. So now when you do a true convolution and let's say you don't do padding, what is going to happen is, so let's say padding is not set over here. So now what is going to happen is you'll end up with much smaller sized output maps, right? The map size won't be the same as whatever your input is. So this is just to kind of keep the output maps kind of the same size so you can stack them up together. Yes, correct. So basically, yeah, multiple terms used for the same thing. Dilation is what is used in PyTorch and in, I think, TensorFlow, but they call it a true convolution. So that's kind of what is going on there. Okay, so yes, correct. Dilation plus padding is what you're going to get it correct. So dilation is what is done. The padding is the extra stuff that you're doing to get it correct in the correct H by W, so that they can be kind of stacked together. In other words, I think this would also work is, let us say we don't do padding. What we did over here with the last average pool, the trick was you ended up with just 1 by 1, right? 256 1 by 1, and then you did an interpolate. And this is what we could have done here also. So let us say instead of getting H by W, you get like H minus 1 and W minus 1. Then you can just interpolate it to H by W. That is a possibility. And that's what, if you remember, dynamic unit also did when we had like odd height and odd width. If you divide odd height by odd width, it kind of gets rounded or flowed rather. And so that's what, when you're going down the encoder, it's fine. But when you're coming back to the decoder, you'll always like kind of miss that 1 pixel, and that will kind of progressively increase as you go up. So the way they solve that is they keep track of every height and width as they go down on the encoder. And in the decoder, if it doesn't match, then you just interpolate to that. And that usually is like 1 pixel or 2 pixels. So that also should work, but this obviously should be faster. Well, I was just kind of thinking about this is like the whole thing with a true convolution is like, maybe we could have written a naive filter which basically said fill every 6th pixel as with a value and keep the rest as zeros. Then your number of computes would have been as bad as if the window size was big, right? But I think the way the dilation is implemented in Con2D is that it picks only the 6th pixel or the 6th pixel every time and then does the multiplication. So this in between stuff is never actually calculated. So that zero is, I think, just like sort of like for us to kind of imagine. Does that kind of make sense? I was just thinking of this like, I don't know if that makes sense to you guys.
Yeah, so the convolution just, it would pick out 9 values, but it's just the spacing between each one is bigger.
Exactly, yeah, something, yeah, exactly like that, yeah. Or in other words, like the same thing when we look at like, when you do a transpose of a matrix in PyTorch, it never changes that in memory, right? The matrix is still kept the same. It's just that your stride and your row stride and your column stride kind of changes. So just the view of the matrix kind of changes. So I think this is, yeah, again, like an implementation sort of trick. Just thought I'll bring that up. So that is DLV3's ASPP block. So now if we bring everything together, so we're using again like a ResNet 18 just to see how things work. So this piece of code is just ResNet 18, how you build out your ResNet with your residual blocks and that stuff. And if you pull all that in together now, DeepLab v3, you get OS 16 is basically, I'm using a ResNet 18 output side 16. So that means H by 16, W by 16, or you can do like OS 8 is also an option. So I pulled this code from, where did that link go? It's attached in the notebook somewhere. This GitHub repo. I really like it because he's really mentioned all the shapes, sizes, and all that. So it makes it a lot more easier to understand what is going on.
Sorry, what was that GitHub repo? Is that the official one that comes with the paper?
No, it's not the official one. The official one has way too much more code than I think is what is required. So it's just too much of stuff going on there. This is not the official repo. This is someone else who's implemented it.
Right.
Yeah. So I have one more block over here, which is basically DeepLab v3 using Torch Vision, which is very straightforward. You can, I think, Torch Vision has an implementation with ResNet 152, I think, and it's pretty straightforward. But then, like, you never do any work, or you're not seeing what is happening. You just call this deep lab ahead and basically pulls in the ResNet 152, and then you just add the ASPP block. So that really was not much of a learning experience for us to even like see code implementation, I mean, details of what they're trying to implement there. So yeah, I mean, like I said last time also, I don't think we should use any of this stuff for training. This is just for like purely understanding stuff, because yeah, there's a lot. First of all, it's just ResNet 18, and everything kind of changes with as you change the backbone and the way the code is implemented. It doesn't take care of any of that stuff. It just naively works for like ResNet 18 currently. So yeah, okay, so that was ResNet. Putting it together was here. Okay, so this basically, this self.resnet at this point of time will be this guy. So this is what we would have got as the output here. You create your ASPP block, which is you create this guy and store off. So yeah, that was basically the init. So if you look at what the forward is doing is you grab the height, grab the width. That would be basically this h by 16, w by 16. A feature map is the output, which is again, which comes out here. This feature map is passed to your ASPP block because that same feature map is used for all of them. You get the output from there. That would be basically here because we stacked everything and put it, oh no, sorry, actually here. We stacked everything, did the last convolve. Everything is pretty much ready because if you remember, our last thing that comes out of our ASPP is actually this output, which was, where is it? Oh no, actually I'm wrong. It just is output of con, so it's just here. Oh no, so actually wait, the concatenation happened here. So all this is done and we did the last convolve. So everything is ready. So you basically have number of classes as the output. So you have those many channels ready and that's all there is actually to it. Why am I doing this interpolate over here? Oh, okay, correct. So when you do this, this output size is basically just h by 16, w by 16, right? You're just performing convolutions. So this is still off by 16. So that's what you're doing over here. You're doing interpolate my last output that came out of this and bumping it up to h by w. And there is a note about this in the paper where they talk about whether we should, so you have two options, right? You either interpolate your output to this size of this, or you basically reduce the size of this and make it the size of that. And they say that the second strategy of actually reducing the size of your input to the size of this, I think works better, if I'm not wrong. And though I implemented it the other way around. Yeah, that's pretty much it. Call the model, cross entropy loss flat, pass it off to your learner and run it. And again, accuracies are pretty close, like plus minus 2%, I guess, with just 2 cycles though, with just 2 cycles, yeah.
Nikhil, there are a couple of questions in the chat.
Oh, shoot, yeah. No.
I can read them for you.
Yes, please.
So the first one, I think you also already answered. So it is actress convolution occurring because of padding.
Right, yeah. So that one is.
And then I think Srinivas did not get the last point you made about not using any of this for training. What was that? Are you saying that your implementation is hard-coded to ResNet 18 backbone?
Yes, sort of, yes. It is kind of hard-coded for a ResNet 18 backbone. I think the reason is the H by 16, W by 16 part of it shouldn't be that hard to like change it up, because the main chunk is really this ASPP block, and that is kind of agnostic to this side of it. So this one at least shouldn't be that hard to change. Whereas like the previous one, the PSP.NET was like very much hard-coded for ResNet 18 because it changes a lot of things, like which layer you want to kind of interject and, which you want to kind of hook into and change things. Whereas this one is a lot more simpler compared to that. The previous stuff, what you asked about training, I don't remember what was the statement that I made. Did not get the last point you made about not using any of this for training. What did I say?
I think you said you wouldn't use this bit of code.
Oh, sorry. Oh, yeah, right. So when Steve asked me about like whether this is from the actual repo, the reason I kind of mentioned that is like you can use this like maybe just to train and see if it works, like what is happening over here. But then the reason why I said is that I don't believe in the code that I've written and implemented. So it's obviously way better to use like that GitHub repo, which we saw with Qbel or any of the other sources where things are already implemented and tested a lot more than this. That was the only point that I was kind of making about not using this for training. Yeah, exactly. More tested code and a much more flexible code for different sorts of backbone. Like even if you go back to like the PSP.NET stuff, which we saw last time from that Arxis repo that we used, the stuff there. So if you actually look at their pyramid pooling module, you'll see there's a lot more boilerplate stuff that is happening, which basically takes care of different backbones. So all these pieces of code that I have actually written here, these are all different if and for conditions based on which backbone you're using, whether it's DenseNet, ResNet 18, ResNet 152, they kind of change. I think because the name of the layers for some reason changes from like DenseNet to the other things. And here also again, for example, like where you would index to get your aux loss, that also kind of changes based on what backbone you're using. Yeah, for some reason, this downsample was indexed as downsample.o was going to be used. So yeah, that sort of stuff is, which I have not at all like taken care of. I just made the code as simple so that we could just read through it and understand what was happening. Yeah, that was the point mainly there. So that is kind of all with DeepLab actually. DeepLab v3 was pretty straightforward and simple to kind of understand. Any questions on that? That seemed pretty straightforward, so I guess, yeah. Cool. Yeah, again, to kind of break that, the accuracy of this was like very, very comparable, or actually slightly lower than the dynamic unit that we saw. But I think dynamic unit is a much more ladder architecture. Oh yeah, that was like 88, or almost 89, and this is like 87.8. So yeah. Yeah, a lot more testing obviously would be needed for that. Quick look at, we implemented unit with the hypercolumn stuff, which again made it even more bigger, and that kind of reduced it 85%. But yeah, I guess this would need more training because it has a lot more hyperparameters. PSP.NET was also somewhere in that ballpark, if I'm not wrong. Oh yeah, and this was like 87 and 86. One was like with that aux loss, one was without the aux loss that we used for training. So yeah, everything is kind of ballpark in and around there. It kind of makes sense. There is nothing like drastically different between them. All of them are trying to implement the idea that you need to look at them at different resolutions, either by using the encoder decoder structure, or you kind of use dilation, which again kind of serves the same purpose. So yeah, that is DeepLab v3. This was kind of mixing up unit with, that is the encoder decoder structure, with dilated convolutions, which was coming from DeepLab v3. So this was something that I was just experimenting and playing to see what happens. Quick look at this. If you look at it again, yeah, for some reason it starts off slower than the rest, but again, kind of gets back to like 85% there. So yeah, let's kind of look at that. All I'm trying to do is, so this self-con 1 and self-con 2, these are the layers which basically was at the middle of the unit when we were trying to connect. So let's actually pull up that. Cool. Are you guys able to see this also now?
Yep.
Yeah. Okay. So that con1, con2 is basically we're talking of this part in the unit. So I removed that out from the unit and replaced that. The whole idea that I was trying was, instead of just bringing stuff from down up, which is basically these blue parts, you're upsampling, right? You're convolving and upsampling and bringing it back. And then stacking whatever you had on this side, and that's the white part, and then you kind of concatenate those two and then perform convolutions. So the whole idea was just why stack what is there right over here rather than perform dilated convolutions of 3 sizes on this. So at this resolution, you're not just going to be seeing what is there at this resolution, but you'll be seeing this resolution plus 3 by 3 convolves at rate 6, 3 by 3 convolves at rate 12, 3 by 3 convolves at rate 18. Same thing over here. Why just see only this, but do a dilation for 6, 12, and 18 and see. So that was just a simple idea that was implemented, and it was pretty straightforward to do. So just to keep the math easy, I said if your number of filters is equal to NF, since I'm going to be adding 4 new things on this side, 4 new dilations. So rather 3 dilations and that 1 by 1 conv. So just to make the stacking easy, I just said that let's divide that by 4, so then I can stack them all up together. So this X is basically cross. So that is what is coming across, right? So that's the cross thing that Jeremy calls it. So across in channels is the same. You're getting output number of channels to be NF by 4. So now when you stack all these together, you'll again end up with like NF number of channels. Nothing else is really changed here. You can see like adding dilation is just 6, 12, 18, 6, 12, 18. Everything else remains the same from before. And what else changes? Yeah, so on the forward, you run your, where is this? You do, so that's how the upsampling, rather than using a naive upsampling, what we do is we do that pixel shuffle strategy. So the pixel shuffle is what is kind of declared here, and that's what you're using here. So you pixel shuffle what is coming from down. So that'll make your size, let's say, increase it by a factor of 2 in height and width. Now, we'll come back to this part. I just referenced this later. And then you're just performing these convolves with different dilations and stack them all up together. These 3 are from the dilation thing, and this guy is from your original pixel shuffle output. So the original pixel shuffle output is this blue part, and this white part is basically that NF by 4, NF by 4, NF by 4. So yeah, this is the part that I was talking about. Like this is what they do, that size check for the dynamic unit to work is basically if your size doesn't match your outshape. So SSH is basically the stuff that you calculated on the left, your encoder side. If it does not match whatever, when you upsample on the decoder side, you just do an interpolate to match those sizes up. So yeah, that's pretty much it. Like, does this kind of make sense? Like, do you guys see loopholes, things to discuss or try, experiment sort of stuff?
Hey, can you hear the non-helium me now?
Oh yes, I can. Yes. This is no fun though.
The non-cartoon. I should trademark the cartoon version.
Absolutely.
Sorry, I have 2 computers going, one sane and another insane, but
okay.
I was thinking of logging off the insane, then I realized, oh shoot, I was the host.
Yeah, you posted it.
If I'd done it, I would have booted all you guys off. So I just saved in the last minute. I had a question though.
Yep.
In this case, just since I was doing all that while you were talking, I may be confused, and you may have covered this already. But are you doing the atrus or the dilated convolution only at the very bottom of the unit?
Oh, no.
Are you doing at different stages along the path wherever it goes from left to right or from
exactly the second one? So that's what. So if you look at the implementation of this dilation stuff, it's in the unit block code. So the unit block code will get called every time you jump from one size to the other. So all these
to the other.
Yeah.
So you're doing it at every level when you cross over.
Yep.
And and the rate is dependent on the level, because you would want to do the atros at different rates at different levels, correct?
But that should probably be a thing that we should like do some evaluation studies and figure out what the rates make sense, what rates make sense. Right now, it is just naively doing 6, 12, 18, 6, 12, 18 throughout.
Oh, it's doing all rates or multiple rates at each level.
Yes, it's doing 6, 12, and 18 for each level.
Okay.
So hence,
because,
which leads to the other point that this becomes a lot more heavier. Hence, I had to drop down like batch size.
yeah, that's what I was
Yeah.
going to say, because in a sense, you would, if the logic or the thinking behind the atros is correct, then the point is you want to combine the detail, but with the macro, meaning with the higher level full image view as well. You want to combine it.
Correct.
And the thing is, which macro level, by macro level, I mean which high or low resolution, meaning higher dimension, higher H by W size, do you want to combine with the at each level is the question. Because
Right.
in your case, it's like the max, meaning it's do all of the rates at all the levels.
Correct. Yes.
Right. So
Yeah.
because the atros thing seemed to say that you could just do, because they only do multiple rates at one
Right.
level,
Right.
so to speak, right? So it's possible that we could get away, like you said, doing ablation studies with just a rate, the rate to be
Right.
determined at each level.
Yeah, that makes sense. Yeah. I think maybe to add to that, I would say like at the higher levels here, you probably want like a smaller rate. No, you want, what rate would be better here? Because you already have like the fine detail
Full
here
image.
because it's a large image,
Correct.
right?
Right.
So you would,
Exactly.
yeah, so you would want like kind of the opposite thing where you would kind of get the smaller resolutions.
Correct. So it would be
encoded.
6 or whatever, right?
Yeah,
Meaning
probably
like
something.
not the 12 or the 18.
Not the 12 or 18, yeah. Whereas on the lower end, you
Correct.
probably want to still hold on to that. Yeah, that could be, yeah, another.
So that would simplify and probably allow you to go to a higher batch rate, right?
Yep. Yeah, that's something, yeah. And that should be pretty easy to try out.
And then given, by the way, and then given, this is the other thing I was saying, that given that the dynamic unit already has attention, you can turn it on and off and see easily.
Another thing actually I wanted to discuss since I said last time we should look at attention, I wanted to look at it. So it looks like attention seems to be only turned on in this conv too, right? And attention doesn't seem to be turned on anywhere else in the code. And that conv2 basically represents this guy, or rather this guy. So that was one thing which I was not able to wrap my head in, like why, I mean, obviously it becomes much more computation if you turn on attention on everything, but like if there was any reason why only this layer, you're basically turning that guy on, or what it was, I didn't understand. If I'm not really, let's double check. I think that's the only place where, yeah, that's the only place in the unit block. And yeah, this is just getting sent to the unit block. So yeah, only that one seems to be getting turned on there, which I did not know why they were doing that. And this was the other question I had, like, why in the dynamic unit call, like there is this evals here. And here also in this middle call, there's an eval here. Like usually you do this dot eval is only when you're kind of at inference, right? You want to kind of turn off dropout, and I don't know if they roll batch norm into conv over here, but I mean, the main reason why you want to do that is so the dropout is not weird during inference. You want to turn that off. So, but this is during training. At every time when middle conv is being called, I don't understand what is happening. Obviously, something is happening and it's training, so it's not like it's fixed. I still don't understand like what the eval is doing over there.
Good questions. I think I'll spend some time, especially the attention part.
Right.
but it may be, like you said, just um, and keep in mind that at least for this particular, the reference he had was again
Right,
attention
right.
implementation. I don't recall, it's been a while since I looked at the paper, so I don't recall whether they, for example, only do it
Yeah,
at
uncertain, right.
at a particular level
Resolution.
or a layer, and therefore, now the one thing is that it is done for every pixel in the image.
Mm-hmm.
So given that it's done for every pixel in the image, and you compute its attention with every other pixel.
Mm-hmm.
So given that, one simplistic reason may not be the right reason, but just thinking aloud, when you get down to the lowest layer is when you will have the least amount of pixels to do that on,
Mm.
right?
Okay.
Because you have the smallest HW at that
Right.
level, right? Because every other HW that you try to do it on would be much, much larger number of
Right.
pixels that you would need to
Mm-hmm.
do it on.
Yeah. Yeah, that's what, yeah, computation wise, yeah, that totally makes sense.
So that computation aspect may, and
Yeah.
again, I'm not saying it is, I'm just suggesting it might be a reason. And then we'll have to look at the reference paper of what the GAN self-attention did, because that's the one that
Oh, wait, hang
Jeremy
on,
pointed.
Srinivas. I think I made a mistake. Sorry, that is on the last unit block. Oh, no, no. So I'm sorry. Take back whatever I said. Actually, this is a unit block definition, and only on the last con of the unit block do you have
Oh, so
self-attention.
that means it is done on
Yeah,
every unit block,
every
right?
unit
It's
block.
just the last
Convo
uh,
of the unit block.
convolution of every unit, which is
Yes.
makes sense,
Yeah,
right?
that makes
So
sense.
okay,
That makes more
okay.
sense.
So
Right.
then it is done at every level as well.
Yes, it is done at
Okay.
every level. Yeah.
So okay, so at least one question
That is,
answered.
yeah, solved. Yeah. This eval
The
stuff, I'm
eval is still
still
a
not
question.
sure. Yeah. And that too, he does well. So if you look at it, so this is the middle conv. And so yeah, encoder is not set. He's just adding batch norm reloads. This middle call is on eval, not sure why. And then this unit block also every time seems to be eval. Not sure. Yeah, that is something which I guess we still have to find an answer for.
But since even in your whatever dilated convolution combined with dynamic unit, it ought to be fairly trivial to turn on self-attention
Right,
versus
right. Yes.
not,
Yes.
and just check. And by the way, at least when I did the self-attention on and off
Mm-hmm.
for the steel defect challenge,
You said you didn't find much of a difference, right?
yeah, marginal difference, and in fact, it was marginally lower, about the same though. I mean, it
Right.
didn't. It's like difference in the third decimal digit or something.
Okay. Okay.
And then, of course, I had turned it on just for completeness with the H column implementation included.
Oh, okay.
So I don't know, like from an ablation perspective, I don't know what would happen if H column were removed and self attention with and without was done on uh, steel. I had done it with H column added to the
Okay.
base dynamic unit and then self attention added or removed, and that didn't seem to make a difference. But that, as we discussed before, is somewhat explainable because H column gets you most of what um, you know, I think some of these other methodologies, which by the way is another thought too, is, and this was something again I was thinking of doing something else, just to, for discussion to throw it out there. If you list the type of things, right? So, and you have tried to combine. I was thinking of just creating that list, which is like H column. H column conceptually, for those who are new, is basically saying I start with the end pixel and then go to the full HW at the largest or incoming input size and take the entire receptive field that is contributing to that particular pixel. So That's H column in a hypercolumn in a nutshell. And so, there is hypercolumn, there is this dilated convolution, there is the,
The decoder structure.
self-attention. Sorry?
Encoder decoder structure and yeah, self-attention.
Self-attention. And then there are some implementation techniques such as, besides the 8-rows convolution, there's the 8-rows separate convolution, right? Meaning like, but that's more a detail to just reduce computation. It isn't
Right. The
changing
depth-wise, yeah.
right, the depth-wise 8-rows convolution. So I was just thinking that you could create a table of these kind of techniques and then see which, and then just
match, yeah, right.
combinatorially apply them.
Yeah. Right. Yeah, the self-attention stuff actually, like you said, like back to the reference to the paper, they apply, they don't justify why it works better at certain layers. They just say that it works better at certain layers, from what I remember. So again, here, like, who knows where you should be applying self-attention to get best results when it's like a unit-like architecture, right? Their structure was not that. So that is again something, yeah, where you can try self-attention or maybe a different convolution layers.
Yeah. And then, you saw this Crazy as just released, but apparently they've been working on it, this whatever thing I posted where they've tried to throw in, but I haven't compared it with HRNet, which seems to be the best in the business right now. So, so any other combinations that, by the way, you were thinking of besides this one that you spoke to?
There was one more. I didn't want my unit on the encoder side to be that heavy. So I wanted to basically, let's look at the unit. My idea originally was to start just with this input image and then somehow get like 3 different rates and then stick it onto this side. So this whole process of this downsampling and learning this convolution was what I wanted to remove. But yeah, I mean, this was a much more straightforward implementation.
3 different rates of what though? 8 rows?
Yes. I'm planning to keep 8 rows. But yeah, like after discussing now, it makes sense. Like maybe I ought to try different rates with different resolutions. That would be a better combination though. Yeah, I guess this opens up like a bunch of things to try and experiment and play around with. But yeah. Yeah, that was the main thing that I was looking at. Actually, since you bring up depth-wise, I just realized that none of it here is actually depth-wise. Or is there depth-wise hidden somewhere? Because that will again.
Is there a depth-wise version in PyTorch that you could use? That you could just replace your.
I don't think does PyTorch have. I think I'm not. TensorFlow has it. But here, I think you'll have to.
Then these guys would have copied it or come up with it equivalent.
Yeah, it says how to modify contour to depth-wise. And that's a very annoying thing between TensorFlow and this. You need to keep. Oh, okay. For depth-wise separable, you can use cons groups parameter. Oh, I see. Okay, that's the way you can do it. But actually, that would be basically doing you'll have to follow it up with a point-wise convolution, I guess. So you still not as simple as like, I guess, just using.
Oh, I see.
If groups are.
But even in, I mean, in TensorFlow, but isn't it at least even when they explain it in Keras, don't they do a 1-by-1 follow?
I guess the explanation, maybe under
I thought in the basic paper.
Because
at least in the explanation paper that I recall, they were showing the 1-by-1, but that doesn't mean they have to do it that way. But
yes, under the hood, they must be obviously doing that, but it's just that it's implemented because I remember for MobileNet V2 is when they actually added this in, because that's where this depth-wise thing came into picture. And that's when they brought this implementation of depth-wise in there. So yeah, this is a much more, and that's the other thing. Like, for example, the way they do padding in TensorFlow is kind of different. Right? You don't specify like how you specify here. You don't say like what the number is. They just take in a string like same. I think if you pass in a string called same, then it does the calculations automatically to preserve the size to be the same. Yeah, that I think like when EfficientNet came out, that was kind of a big deal because it came out with obviously TensorFlow, and then when they ported it over to PyTorch, their implementation of padding and the implementation of padding here was slightly different. So results were different, and there was one big thing about that. So yeah, those are kind of like the implementation details that were there. So yep, that's pretty much it. If anyone else has questions, I don't have HRNet fully done, so I think we can discuss the paper.
Did you actually run your UNet with dilated convolutions?
Sorry, can you repeat that again, Stu?
Did you run? You didn't show us through the results of it.
Of DeepLab v3?
No, of UNet with diluted convolutions.
Oh yeah, I showed you. Like it shows up to be there almost. Wait, this is the one, right? Oops. It does slightly bad. I think it gets me like 85 or something. For some reason, I have one with 88. I don't know which one this is. But yeah, with the dynamic unit ASPP, this is the one where I use and I end up with like 85. I think this was the run I did yesterday. That's why I remember 85, but somehow. Oh no, this is dynamic. Oh, so that's what I was comparing it with default dynamic unit, and that gives me 88. So yeah, it's slightly low. So yeah, but yeah, obviously this is
the
a lot
ballpark though, right?
Sorry?
I mean, for still in the vicinity
yeah, kind of. I agree.
Meaning it's not like 60s or 70s,
Right,
or
right.
I mean, it seems like with some tweaks you could get it up there.
Probably, yeah. But the biggest thing was if you run through this notebook, you will see here. HyperNet plus UNet plus hypercolumn. Also, there's a slight change in size that I had to do. And when you're running through this code, if you wonder why this is happening, it's because hypercolumn has this problem where I haven't taken care of the interpolation when the sizes are odd. So if anytime you pass in an even size, it'll be fine because it'll divide by 2, divide by 2, divide by 2. So there's no problem when it's coming back up on the decoder side. So that was the missing detail in the hypercolumn. So that's why I had to change the size to that. But with unit and dilation, I had to drop, what did I do? Oh, actually, I was just greedy. So I dropped both. I dropped size by 4 and I dropped the batch size by 2. So maybe that's why the first one performed that bad actually.
Because batch size of 2 would be very...
Yeah. Which actually made me stumble across. So we've been discussing quite a bit about like this issue with, especially with segmentation, where you have this huge image, you need to keep so much more stuff in memory because you need to kind of reconstruct back your image and then back propagate from there. So batch norm is always going to suffer because your batch size is going to be small, right? Or your image size becomes really tiny. And there was this, I don't know who shared it, I forgot, on Twitter, where is that? I have the paper here. Online normalization. I haven't gone through this, but yeah, if someone is interested, you can kind of look at that. And they basically, in essence, does not use batches. It is as accurate as batch normalization. So that is basically the bottom line that, yeah, it was very interesting. And they have a lot of studies, ablation studies at the end of it, which kind of show that with ResNets, how they managed to get very similar results. Anyway, this is, I think, yeah, just wanted to kind of point that out. Like with
no, that'd be great. If you could do 2 things whenever you have time, is post this reference thing on Slack and also your notebook on the updated notebook on Slack.
The notebook, yeah, right, yeah, I'll do that.
A question. So the online refers to what? What is the term online in there? What does that mean?
The online, I think, refers over there that it kind of concludes on the fly. That's what my understanding is. So it kind of like holds things in like that. Saying it in memory would be wrong because then I think I'm conveying something different. It's more like, yeah, that's what I understood from the online normalization, is that it kind of does it on the fly. So yeah, I guess, yeah, I haven't completely gone through that, but yeah, it's something which we should totally look at. I think, yeah, especially with segmentation stuff, I think this is really helpful.
Yeah, it ought to be, but it's good to learn this since we were just in 224N talking about layer norms. So this is yet another norm, I guess.
Correct. Yeah, like, yeah, exactly. Yeah. So, yeah.
Great. Okay, two requests. One is so next week, just for context, we'll if there are any more ideas, Rekil, you have of things to try or something, we'll start with that and then quickly move on to HRNet paper, since that's kind of the last of the three that, and I think I posted and shared that if you haven't on Google Drive with my comments
Right.
marked up, and feel free to chime in there. We'll do that and we'll discuss any other ideas, Rekil, or even this paper if at the time to have gone through it and see what the improvement they suggest or how it's better. And then the second request from me is potentially for everybody joining to think about, since we are almost, we've been, I checked something and we've been at it for like 3 months, 4 months plus. I think we are winding up on this particular competition. So my request is to start thinking about the next Kaggle challenge that we would want to uh, discuss and try out on the Kaggle group. And I think I've seen some requests both to potentially do a variation. At least the last time when we moved on, we went from just classification to segmentation. We could potentially continue to object segmentation and or like object detection type of things, but they also received multiple requests from people to consider NLP type competition. And I think there is a Q&A competition in NLP that just ended or was going on at the time when we were doing this, so should have ended by now. There was another one that I think NLP related that Mehul had pointed to as well. So my request is, and I'll post an update on Slack, a request as well, is to think about what would be a good next thing we should dive into. Keep in mind that, typically we choose or prefer recently ended competitions primarily because it allows us to collaborate without worrying about sharing code or discussing things within. Otherwise, there are limits on team sizes and stuff that intervene with that kind of an approach. So we typically prefer things that have recently ended, because the recent ending also gives us the uh, fact that most of the kernels and other things that people have provided continue to work, as we saw even in Steel, even though it had recently ended, and I think Steve found this out, was the data or the updated thing we had to deal with was different from when the competition was live. So to prevent those kind of issues, which we can't eliminate as we saw, but we try to do competitions that have recently ended. So with that, so I'll post a request on Slack as well later today, and if people can chime in with suggestions, then maybe we can create a kind of like a voting mechanism or whatever of what people's interests are. And not a rush. We still have 1 or 2 weeks to go to discuss and along this itself, like HRNet is there, and maybe one summary of what all people have tried, and then we are done with it. So those would be my requests.
Yeah.
Any comments or suggestions?
No, the voting sounds good. I think one interesting thing I noticed about the NLP and TPU competition is it's like NLP TPU getting started, and I think I saw it for the first time. They have something called a rolling leaderboard. So there's no prize money. So, but it looks like every every 2 months they reset the leaderboard, and I've never seen that before. But in a way, it's very nice. It's like it's just an active competition, and we don't have, yeah.
Yeah, the only thing with active thing was those other restrictions that I talked about, which is the reason we have shied away from it, because we don't want to get in trouble for doing anything, and we want to be fully. The purpose in this case is as much to learn and therefore share and look at each other's code and all that, rather than a formal competition where they limit that to within the team constraints.
I
So
see.
they when we started this whole thing, we looked at it and they said, and there were rules people pointed to, and I've looked at it myself, which is you have to have a team of not more than 5, and you should not share anything you do. I mean, people post kernels, I guess that's different, but you shouldn't discuss or share code beyond the 5 and things like that. So we just didn't want to suddenly have somebody post saying, "Oh, look what you guys are doing," blah blah blah, and we are covered completely if we then only discuss what's already ended.
I see. Yeah, I think. Okay. Yeah. No. All valid point. I think like because Kaggle gives 2 types of rewards. Like they give some tier points, right? Some ranking points, and
Right.
I think this one has no points. So we can just check the rules, like what happens when.
That's what we'll need to do. If we check the rules and there aren't restrictions, then by all means.
Yeah. Yeah, because they started a new one called similar, like everybody's like struggling with GANs, like so they did getting started with GANs, and I think it's the similar idea, like no points, no ranking points.
Yeah, the other, I mean, since we're on the subject, the other idea that I think Steve had suggested, a couple of others had mentioned interest in NLP, and there was a Q&A competition very similar, and I thought that would also be interesting, because in the Stanford CS 224N we are discussing Q&A. That's like the default competition that or default thing that was posted, and and almost, I don't know how similar it is, but it is a Q&A competition that I saw that came up on Kaggle as well, NLP related. So I thought, it's directly applicable. 224N is almost, well, there may be like half a dozen more lectures, but BERT transformer will be done in the next 2 weeks. So what we need to know to apply most of the techniques we would have already covered. So it ought to be a good, hey, you listen to all the theory, now try some practical stuff.
Oh, sounds great.
Right. So that's another, and there may be others too. So that's why I'd encourage people to look at and post what ought to be considered for, and we still have about a couple of weeks, so that'll give us time to pick the next one after some discussion. And I think Mehul kind of trailblazed this path. Typically, we take a week or so even after we choose, or we choose 2 or 3, because I think, as Mehul demonstrated, we, in fact, even in this steel one, if I recall correctly, and Mehul can correct me if I'm wrong, but we went down a path of selecting something and then we backtracked because he made some submissions, they didn't work, they took too long to come back. Things like that are important if you're going to really learn from the effort. So I think we should have a short list and try things out before we settle on the final choice.
Right. I think, yeah, before steel, when we did protein, we had that problem, right? We did the
something else.
Yeah, the I one, glaucoma one, and it would never, you submit it and the results don't come back for 12 hours.
Yeah.
It's horrible. So then we moved to protein. Yeah.
Protein. Yeah. So that's a good one you highlighted, like, hey, without feedback, without prompt feedback, the purpose is defeated. So I think those kind of checks, even after we choose one. So even in the path, if people have actually tried submitting and played with it somewhat before proposing, that helps. as well. So one last thing, I think I don't know whether he's still online, but and whether this was Zoom's capability that did it or something else. But you know, for some reason, as I was struggling here, Joseph became the host, which was kind of interesting. Whether Zoom failed over and we are still on, Joseph. Thanks. It seemed to have gone to you as the host and then returned to me as my computer recovered. So, which was either Zoom's failover capability or some other miracle that occurred which helped the session to keep going. So, thanks, Joseph. I don't know whether it was.
Yeah. So I'm sorry. What happened?
So actually, as I said, there were all kinds of issues with the computer I normally used to log in as host, and I was logged in there as host, as Team TWIML host, and I lost the connection there. And at that point, Zoom told me that you had become the host.
Huh.
And I was pretty impressed and surprised that it actually failed over to you. I don't know whether you were logged in as yourself or logged in as into TWIML when that happened, but it failed over to you. And I'm logged in as me on this next computer in order to allow me to talk without being helium inspired. But
yeah, I mean, I was logged in on TWIML, so maybe that's what happened. It just automatically.
Yeah, and it failed over to you automatically. And then later, when things on my other computer corrected themselves, then it went back to me being a host, which I thought was, if it's
very smart. Yeah.
Zoom capability, then it's a very smart thing that happened. So just so you know that in case if somebody else were to be logged in, it seems like as long as they're logged in as TWIML host, it does a failover, which I thought was very, very cool.
Yep.
So thanks for that. Okay, thanks everyone, and thanks Raquel for taking us through the ideas and the presentation. If you can post the links, that would be really great. And we'll start with Raquel and move on to HRNet in the next week's discussion. And hopefully my helium self will dissipate by then.
Yeah, sure.
Okay.
With the online normalization, if you guys have time, just to have a quick look, just so we can discuss next time whether it's worth going into it in more detail or not. There doesn't seem to be so much of news about it, so there must be something fishy about it, I guess. I don't know.
Yeah, sometimes it may just be, as Jeremy often says, right, that it's too fiddly.
True.
And too many things to tweak. He kind of says, yeah, but, and that is true. In many cases, things come up which seem really good, but it's so fiddly that it doesn't get. But sometimes, like the Smith guy's paper, it's just that it doesn't come from the big guys, or it doesn't get the attention it deserves, and it may be that too. So we have to see which of the two classes it is.
Yep. So yeah, just a quick glance, and if something looks promising, then we can kind of
yeah, or even just quick here's what it seems to do, and that would be great. Okay.